Hello and welcome. In this video lesson, we are going to take a look at the method of proof by induction. So there are often a lot of claims that cannot quite be proven with techniques such as direct proof or even proof by contrapositive, and we'll look at such a case. But let's go ahead and start off with an interesting example. And throughout this, I would like you to pause and see if you can think about these individual problems on your own before you hear me solve them. So first of all, let's consider a 2x2 checkerboard. That means it has 2 rows of squares and 2 columns of squares. Suppose you place a single square tile on one square from the board. Assume that an L-shaped piece consists of 3 individual squares as shown. The question is it possible to cover the remaining board with non-overlapping L-shaped pieces? So what we're saying for a 2x2 is for a 2x2, we want to ask, can you take a 2x2 square and cover up any one of them and then use the L-shaped pieces to cover up the remaining ones? So we can imagine we can rotate this, we can flip it, we just cannot change the orientation of these 3 squares. So first of all, if I cover one of these up, it shouldn't matter which one. Suppose I cover that one up. Well, then I could take this L-shaped piece and I could rotate it so that it looks like this. So I suppose that would be a rotation of about 180 degrees. And then I could, or I'm sorry, not like this, not quite like this. Let's move this guy down here. So rotate it a little bit more so that your L-shaped piece looks like that. And I'm just going to go ahead and draw the L-shaped piece like this because that covers 3 squares in the shape of an L. So far we know that we can do it for that 2x2, but that was assuming that the square that was covered up was in that corner. Well, on another 2x2, and once again, I would like to ask you to pause throughout this to see if you can make sense of it before we go and look at it together. So suppose that that square that was covered up was here instead. Well, once again, now in that case, I could just use the original L-shaped piece and I can cover up the remaining squares. Now they can't overlap, so that means I can't have part of my L-shaped piece in the green area, which is considered to be the square that is covered up. And I can't have a part of the L piece hang off the board either. Well, that's not the only case, because somebody may say those 2 cases are great, but what about the third case where I cover up the square down here? And of course, once again, we could say, well, if you rotate this thing 90 degrees, then you can cover up those 3 remaining squares with that L-shaped piece. And finally, the last case of the 2x2 would be where we covered up the bottom left square, which is this guy, and then to use L-shaped pieces to cover up the remaining one. That's great, that's for a 2x2. But what about a 4x4? Well, for a 4x4, we'd probably have to do some convincing of ourselves in order to establish whether or not that's true. So let's move on to a 4x4. So for a 4x4, I'm now going to have 4 rows and 4 columns. And once again, I'm going to try to do the same thing. But you can see that this is going to get quite more, or considerably more costly to deal with this size checkerboard because now we have 16 squares. So I really encourage you to pause the video and think about this and see if somehow we could relate this back to the 2x2 case to see whether it's possible for a 4x4. So first of all, we have to cover up any square inside of this. I should be able to cover up any square. So for instance, I should be able to cover up this square right there and tile the rest using these L-shaped pieces. So I can kind of start and I can kind of do that, and I can do that over here, maybe this over here. But I see I've gotten myself into a little bit of trouble because, of course, now I still need to cover up this square and 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 this square, but I can't do it with L-shaped pieces anymore because I can't move the individual squares. It has to be in that L-shaped piece. So unfortunately, I'm not going to be able to do these do these 4 squares or these 2 squares. But if I begin thinking about this in a more careful way, I can actually see that a 4x4 is really 4 2x2s. And if I really think about this one down here, this bottom left corner, as one of the 2x2 cases from above, oh, hey, look, that matches the second case. And so what I can do with that 1 square is put an L-shaped piece there. And therefore, I have completed at least one of the 3 2x2s within that greater 4x4. But then I have 3 remaining 2x2 cases, and none of those look quite like the ones up here. But it would be really great if I could turn all 3 of those 2x2s into situations where exactly 1 square is covered up. So let me do this. Let me put an L-shaped piece across the 3 2x2s like this. And now imagine that really this L-shaped piece, just all it really did is covered up 3 squares. And so as a result, I now have 3 new 2x2s, each of which obviously have to match one of these 4 2x2 cases here because these all started with 1 square covered up. So now here I can put an L-shaped piece there, an L-shaped piece there, and an L-shaped piece there. And let's just consider one more 4x4 case, because maybe what I did was really made this somehow a special case. So here we go, roughly our new grid. And so once again, I'm going to continue thinking about this as a set of 4 2x2s. And now if I cover up any other square, I don't know, let's pick this one up here, then how do I tile the rest with L-shaped pieces? Well, of course, this top right 2x2 looks like one of my cases from up here. It looks like this one. So, it looks like, yes, this one here. So I can just put an L-shaped tile there. But now again, I have 3 more 2x2 cases that do not have 1 square covered up. However, if again I link these 3 with one L-shaped piece like that, now I've essentially created a similar set of 3 additional cases where there's exactly 1 square covered up in each 2x2. And now you can see that I can cover up those two, and those 2. Let's just consider one more case. So if we, again, look at something like a 2 to the third by 2 to the third, we ultimately want to ask, can you prove this is the case for any board with dimensions 2 to the n by 2 to the n and 1 square covered? It is safe to assume that n is an integer, that n is in the set of integers, and we want to be able to justify our reasoning. So here is a 2 to the third by 2 to the third checkerboard, and you can see that this gets conceivably more difficult because it's larger. But let's go ahead and again think about dividing this 8 by 8 into 4 4x4s. So it'll look kind of like this if I create a division there and a division down the center. You can see that really what I have is 4 of the previous case, the 2 to the 2 by 2 to the 2. A 2 to the 2 by 2 to the 2, i.e. a 4x4, consisted of 4 2x2s. So an 8 by 8 consists of 4 4x4s. And once again, I have to be able to arbitrarily place cover up any one of the squares. So let's say this one right there. If I covered up that square, how would I tile the rest? Well, this 4x4 is already taken care of by virtue of the fact that we know that we could break this up into 4 2x2s. So let me do that with a green pen here. So if I broke this up into 4 2x2s, we see that that is exactly one of the cases that we know how to handle in the 4x4 case. So now I can take my L-shaped piece and perhaps cover up these 3 squares here, again creating 3 more 2x2s that all match the structure of this initial 2x2. And so now I can put my L-shaped piece there, put one here, put one here, and put one here. And the problem is that that took care of one 4x4 case, but I have 3 more 4x4 cases that do not have a single square covered up. But guess what I'm going to do? I am going to link the 3 squares via an L-shaped piece. Each 4x4 is going to have 1 square covered up by this L-shaped piece, and now I have created exactly this case up here where the green shading is just represented by the components of this L-shaped piece here. So now I can once again create my 4 2x2s. This 2x2 here, I'll cover up those squares, and then again I'll take an L-shaped piece and connect the remaining 2x2 squares and be able to take care of those guys. And I'll do the same thing here. Here's a 2x2, take care of that. I have 3 more 2x2s. I'll connect those with an L-shaped piece, fill in the rest. And once again here, this 2x2 I'll fill in like that. I have 3 more 2x2s that need to be taken care of, and I'll connect those like so. And you can see that it is always going to be possible because I can always create the next case from the previous case. So what can you say if the board, well, we're not going to worry about that question right now, but the question is, can I do this, continue doing this for larger n? This kind of proof is a little bit different than other proofs that we've considered because we're trying to ask, can we do this for a 2 to the n by 2 to the n for all n? For all n. Okay, so when you're trying to prove something like this, it's difficult to do because there are infinitely many integers. And as a result of there being infinitely many integers, you would have to consider infinitely many checkerboards in order to prove this. Unless you could somehow reason through, well, here's evidence that it works for the smallest case, a 2x2 case, and then use a couple of examples just to yourself to be able to reason that you could extend that principle, looking for a pattern of how the previous case connects to the next case. So let's say something like this. Suppose a 2 to the k by 2 to the k checkerboard can be tiled this way for some arbitrary integer k. In other words, what we mean is that we have some 2 to the k by 2 to the k board. Now, I don't know what k is. K could be 10 or 15 or 30. The point is that this is some arbitrary, meaning we're not specifically saying this is 2 to the 5th by 2 to the 5th. Because if we did that, then our reasoning would only apply for a 2 to the 5th by 2 to the 5th. So in other words, suppose that you can tile this 2 to the k by 2 to the k, that you can completely checker this, this size board. Okay? Now, the pattern that we're noticing is this. Consider, and notice that we're saying assume, suppose a 2 to the k by 2 to the k checkerboard can be tiled for some arbitrary integer. So assume that this one can already be tiled. Consider k plus 1. So now we are looking at a 2 to the k plus 1 by 2 to the k plus 1 checkerboard. Now we've already kind of reasoned that if you increase the exponent by 1, you just create 4 of the previous case. And you can see that here by properties of exponents that 2 to the k plus 1 is 2 to the 1 times 2 to the k. And normally when we multiply bases, we add their exponents. And this right here is 2 times 2 to the k. And if I rearrange this as just 4 numbers being multiplied together, you can see that if I bring the two individual 2's out front and just leave this as a 2 to the k times a 2 to the k, then I basically have 4 2 to the k's by 2 to the k. And so because I'll have 4 2 to the k by 2 to the k, so we will have 4 2 to the k by 2 to the k's. And so now when I consider this 2 to the k plus 1 by 2 to the k plus 1, I'm going to see it as this whole thing here is 2 to the k, and this whole thing here is 2 to the k. But if I split this thing down the middle and split it across the middle like this, then each of these right here is going to be a 2 to the k plus 1 by a 2 to the k plus 1, because we're going to have 4 of those. And now suppose that any square is covered up. So suppose there's some square covered up over here. Well, I already know that this I'm sorry, I made a mistake in my, this should be, these are 2 to the k's, and the whole picture is 2 to the k plus 1. And this is 2 to the k by 2 to the k. Well, I already know that we've said that suppose we found some 2 to the k by 2 to the k that can be tiled if you cover up just one of the squares with that green shading. So we already know this one here can be tiled by our suppose that a 2 to the k by 2 to the k can be tiled. But now I have, once again, 3 more cases that are 2 to the k by 2 to the k, but do not start off with having one square covered up. However, if what I do is I once again use my observation that now if I connect the top 3, or these 3 little squares that'll be here, here, and here with an L-shaped piece, I've now created 3 more 2 to the k's by 2 to the k's that look like the 2 to the k by 2 to the k that has one square covered up, and we already know from our suppose that it's true that 2 to the k's can be tiled completely with just one square covered up. So what have we done here? We have shown that basically that if it's possible for some arbitrary case for that checkerboard to be tiled, then it is also possible for the next size up to be tiled. So if any 2 to the k by 2 to the k checkerboard can be tiled with one square covered up and then the remaining L-shaped tiles, we have proven that a 2 to the k plus 1 by 2 to the k plus 1, that is the next size up, can also be tiled. And that means that if you think about the logic, as long as we've proven it for the 2 by 2 case, and we've just established the fact that if it works for one size, it works for the next size up. So we've inductively said that if it works for a 2 by 2, which we've shown that it has, then it must also work for a 4 by 4, because of the fact that we've shown that if it works for the smaller dimension, by this generalization, it works for the larger dimension. Therefore, that automatically states that this works for a 4 by 4. And guess what? If it works for a 4 by 4, if that's our 2 to the k by 2 to the k, then it works for an 8 by 8. And if it works for that 2 to the k by 2 to the k, then it also works for a 2 to the 4th by 2 to the 4th, or a 16 by 16. And we're sort of knocking down all the dominoes by making this general argument about, having made this general argument about being able to tile the higher sizes. So hopefully that gives you a little bit to think about. We are using some general reasoning here, which makes it challenging, but let's think about the logic of what we've done. and why we even need to think about this logic. So many times in coding theory, we write a function involving loops that we claim works for all possible n. For instance, consider the following pseudocode. Nothing interesting happens here really, except we assign 0 to a variable called total, and then we have an index that goes from 1 all the way up to some value n. And every time this thing iterates, all that's going to happen is the total is going to get multiplied by the current value of I. So this is so uninteresting, in fact, that the first iteration total will be 0 times the first I, which is 1, which is 0. And then the second iteration total will take the current value of total, which is 0, and multiply it by the next index, and still producing 0. So basically this is a pretty useless function. But suppose that I wanted to say that this function will work for any value of n, that it basically will multiply all of the totals together. Well, it's easy to claim that, right? That, well, it's a loop, it should always work, but we need to provide some justification, especially as computer scientists. One of the important jobs is to be able to argue and effectively convince people that this code will work no matter what values we feed it. So we make the claim that this block of code will multiply all the integers beginning at 1 and ending at the integer value n. We can certainly test this on a variety of n values, and it may seem obvious to us that it works, but how can we be sure that it works for all n? That's the argument here, that we're trying to prove things that work for all n. This is a justification for which none of our proof methods will work, since there are infinitely many values of n that the user of this block of code may potentially choose. Before we get into it, let's develop something we want to prove.